Our moderator for the next session is Pedro Alvarez from Rice University. And Pedro, I think you were a Clarke Prize recipient, were you not?
That's right, yes.
Welcome, Pedro. It's always good to have you back.
Thank you. Well, good afternoon, everybody. I would like to invite you to take a seat, please, as we proceed to the third session today about new and innovative sustainable technologies. As you all know, the importance of clean water to global health and to economic development simply cannot be overstated. But unfortunately, providing clean water in a reliable and affordable fashion is becoming increasingly difficult as the demand grows with the population, as water pollution becomes more complex and more difficult to mitigate, and as climate change, with more frequent droughts and saline intrusion in coastal areas, threatens to exacerbate freshwater scarcity. And this underscores the need for technological innovation. And environmental biotechnology can play a very significant role in these treatment trains to allow us to, how should I put it, tap also unconventional water sources and enable also safer wastewater reuse. Today, we are very fortunate to have gathered three of the top and most influential modern environmental technologies in the world. They have made tremendous contributions to the practice and pedagogy of water treatment and reuse. And to lead this off, I'm very honored to introduce Professor Perry McCarty from Stanford University. He's the 1997 Clarke Prize winner. He has won many other awards, including the Tyler Prize, the Stockholm Water Prize, which is the equivalent of the Water Nobel Prize, I would say. But also, he has made a tremendous impact on environmental engineering academia by populating top universities with his students. I am proud to count myself as one of his intellectual grandchildren, as is Joe Hughes. I don't know if he's still in the audience, and Bruce Ritman also is, his student. So with that, please help me welcome Perry McCarty.
Thank you, Pedro. It's certainly my real honor to be here to talk with you this afternoon. I want to tell you about the treatment plan of the future and for wastewater. About 3 years ago, I had the honor of being here at the Clarke Prize conference to tell you about the beginning of this study on an anaerobic bioreactor, membrane bioreactor. We had been conducting laboratory studies. They looked very promising. We had started a pilot study on it at that time. And so now we've completed that pilot study. We have others beginning. And so I'd like to tell you about that particular one and where we're moving on this. So George Banaglos talked about, the paradigm, called the paradigm shift, that instead of looking at wastewater as a waste, it's very important in the future because of our limited world resources, growing population, and economic development, that we look on all our former waste as resources. And here we've been talking primarily about wastewater as a resource for water. But that's not the only aspect of the wastewater that's important. George also mentioned the bioenergy. And because of aerobic treatment, the aerobic treatment system we have today, and many of the advanced treatment systems that we're having, all keep on using more and more energy. But the reason we're having climate change is because we use so much fossil fuel and so much energy that we've got to change. That's where the big shift got. We got to stop using energy. We've got to find processes and ways we can reduce energy. In fact, in this one, we produce energy rather than consume it. Other thing is the nutrients and wastewater. And I just want to say the ammonia and organic nitrogen in wastewater, which we get primarily from the food that we eat, it took more energy to bring that nitrogen out of the atmosphere and convert it into fertilizer that we use than to operate a whole aerobic activated sludge system. It's more. And so what do we do when we come to the treatment plant? we waste more energy and send it back up in the atmosphere. Does that make sense? When we're trying to reduce energy, and that's something I think we've got to really think about and change. And of course, there's other potential products that we get from it. Well, the process that we developed was my colleagues and one of my former students, Jae-ho Bae in Korea, Inha University, asked me to join with him and put in a proposal to the federal government. They had a program they called World Class University Program, where they were funding senior people to come and work with them for a 5-year contract, which I did about 2 months a year. And what is interesting, Professor Kim there, he came with, he's with membranes, and I got one of the students, Chung-Mo Chin, who's been so instrumental in so much of our work. I just wanted to make sure that his name was on that. Well, something I'd always been interested in to see, well, we've been making great progress in anaerobic treatment. So now today, if you do an industrial waste, organic waste, a couple thousand milligrams per liter or so, if you don't use anaerobic treatment, you are wasting your client's money, you're wasting energy, and so forth. It is so much better than aerobic processes in all aspects. But the question is, and the common belief has been, that you can't treat a waste anaerobically. In essence, in high concentration, it's a high temperature, and those are requirements that people said in the past. Well, there's a lot of evidence that said that we could probably do better, and the question that we asked is, well, how much better can we go? And can we really, if we make an effort to treat it, wastewater 100% anaerobically and achieve the energy production, while at the same time meeting effluent quality standards and at a lower cost than conventional aerobic treatment? Now, the process that I really liked is this one. There's a fluidized bed anaerobic treatment, and in here there's a little granular activated carbon, maybe a millimeter in size activated carbon. They have recycled the water and fluidized the GAC, so it's floating in there. The bacteria find this is a great place to colonize. Now, the nice thing about that, you get this colony of organisms on the activated carbon, and you can put the wastewater very, very rapidly through, very rapidly, in minutes, and still keep the organisms, all of them, in the reactor. So this is the kind of process we need. Now, this just happens to show 2 of them full-scale industrial wastewater treatment plants in Taiwan. I just want to indicate it's a standard technology. There's nothing new here. All we're talking about is using it for a more dilute wastewater. There's several, actually, in Taiwan of this kind. So what we propose to do is to put it first, the one reactor on the left, is just that one. It's a conventional fluidized bed anaerobic reactor producing methane. Bacteria growing on the little particles of granular activated carbon. And then we took the effluent from that, and since Professor Kim came, we said, well, why don't you we'll take one of these and put in some membranes and just see what would happen. So in the second one, we put in the membranes as shown there, and the granular activated carbon was just rubbing on against the membrane as it was being fluidized, and we found that this reduced a major problem, and that is fouling of the membranes, reduced it right away, and at a much lower energy cost than in the traditional ways of using this anaerobic system. So I just want to show a little bit about this. Now, what's different here, that was the new concept, was that in traditional membrane bioreactors, they use gas barging. This is in where you put the membranes right in the reactor. And here they use, in aerobic systems, they use a lot of air. In fact, this is where the big energy cost comes from. A lot of air to shake the membranes. They prevent the fouling by just shaking them real hard. In our system, which we call particle barging, instead of putting all that air in, which is very high in energy, we just let the GAC, while it's treating, holding the organisms and treating the wastewater, at the same time it's rubbing against the membranes and reducing energy. So from our laboratory, we then built this a pilot scale in Korea, and the one on the left side there is the first reactor, the fluidized bed reactor with just the GAC in it. And the one in the middle reactor, is where we put in hollow fiber membranes and put with the GAC. So that was the second reactor. Now on the far right there we just opened up the front of it so you could see the hollow fiber membranes inside. So that reactor, then we had GAC up to about the 50% point, and then we fluidized it to cover all the membranes. We treated this waste at the Busan wastewater treatment plant in Korea. It's a very large treatment plant, and we took the primary effluent. So we're treating all just the primary effluent. It had a COD about 300 and a BOD around 160. And in the first reactor, we used a 2-hour detention time. And in the second one, we started about a 2.6-hour retention time. We ran it for 2 years. And over that period of time, even with, we had no chemical cleaning. Now, chemical cleaning is a typical thing to do maybe once a month or so in an aerobic membrane bioreactor. We hadn't designed the reactor to find out exactly how to do that, so we ran it for 2 years without any chemical cleaning. And during that time, the membranes, the fouling got such that we had to reduce the flux through the membrane, so we increased the detention time. Nevertheless, the total detention time we're talking about is sort of in the 6-hour range, which is typical of aerobic treatment system. The flow rate through the reactor here then is shown there about 4 to 7 cubic meters per day. So what do we get? Well, in Korea, now this is the wastewater temperature, and it varies. And at the top of this slide, you'll see a temperature range. So in the first little part, when we started, there's a wrong time to start an anaerobic system because it was a winter's approach and summer was over, the fall was there, and the temperature of the wastewater dropped from 20 to 15 degrees. But we were just starting up the reactor. It takes a long time for the organism to grow. Anaerobic organisms have a very long doubling time, and especially when the temperature is lower. But nevertheless, probably a lot of this was initially some absorption because we were getting almost 85% on average. And then it dropped to winter. Temperature at the top you'll see is 14 to 8 degrees. We're getting about 85% removal. And then we come to springtime, temperature 15 to 25. We started getting increased efficiency, our 90%. Summertime came in Korea, it's 26 to 32, and you see now we're getting 97%. Well, this time, the summertime is required so the organism to grow fast, get attached to the GAC in a nice large culture of organisms, and we see got efficient removal. Well, then we come the next fall, and you see now the next fall, we're getting over 95% removal, and even in the winter when the temperature got water wastewater temperature down to 9 to 13 degrees, we were still about 93% average BOD removal. So we see once you get it acclimated that even in the wintertime, which is actually was a very big surprise to me as well as to all of us, that we could still get such efficient treatment process. And if we look at the effluent BOD, we can see that EPA standard here, we got the 30-30. Well, you know, even when we started, we got that most of the time. But by the time we got adapted through that first summer, and then it went into the fall and the winter, we see that over on the far right side there, that even in the wintertime with temperature in the 9 to 13 degrees, we still only had around 8 milligrams per liter of BOD in the effluent. So this is a very good quality effluent, short detention time. So this is one of the big things. So this is an energy neutral system, not putting any energy into it, and we're getting that kind of removal. But one of the biggest cost savings from this system is shown here in the Biosolids Production. Shown here the anaerobic versus the anaerobic on the left, the aerobic on the right. Now they were both doing primary treatment, so the amount of sludge they would get from primary treatment, shown in the blue, is about the same. But it's the secondary treatment. Since most of the methane energy in the organics goes off as methane, there's little for the organism to grow. So organism yield is very tiny. And the main problem with activated sludge is all the waste biomass is produced. And they're very fluid, it doesn't settle very well. And we can see maybe about a quarter or 1/5 as much biosolids produced in that secondary process. So overall, anaerobically, we get about half the biosolids. A normal activated sludge plant, biosolids handling is often talked about as being 40 to 50% of the cost. And here we've cut that in half. So I think this is one of the big cost savings besides energy. Another surprising thing, excuse me, we had at the Mitch at Stanford and Dave Sedlak at Berkeley said, gee, they were kind of interested in looking at the possibility, let's look at pharmaceuticals and contaminants of emerging consumed. What happened in the anaerobic systems obviously would be worse than aerobic. So the full-scale plant, highly efficient plant at Bouchon aerobic system, we said we got samples from that, and also took the samples for the effluent there and the samples from here. And what you'll see is the influent is shown. These are a range of the ones that they found. And the blue one shows this is the secondary effluent after treatment. What's going into the plant is the primary effluent. And then the effluent, you see a lot of red. That's the aerobic system. The yellow, which you can hardly see, is the anaerobic system. And this is after a year and a half of operation when we looked at these samples. We got 96% median removal of the pharmaceuticals in the anaerobic system and only 76%. This is confirmed by some colleagues in Taiwan independently. Well, they did a similar study and with the ones they found, and the simplest thing, we don't quite understand why it's removing. We've got a speculation, we got to find out, but it was obviously, when we look at trace chemicals of this kind, the anaerobic is doing very well. I just want to compare, this is an anaerobic membrane bioreactor. If we look at aerobic membrane bioreactors, because it takes so much energy to keep the membranes from fouling, it's about 1 kilowatt hour per cubic meter. And what we were finding in our system is shown here. For the anaerobic MBR system, we see the energy requirement. The fluid, first one, hardly used any energy, certainly less than a tenth. But the anaerobic membrane bioreactor, and this is primarily to fluidize the GAC, was about 0.21 for a total of about 22. So about 22% of what we had for the aerobic system. But the energy, the methane that we produced and converted to electricity. Now this is how much energy, electrical energy we're talking about. And we take the methane that was produced and burn it, convert it into energy. It would give us about 0.13, not quite enough. But if you take the primary, the methane from all that primary sludge, we would double that amount of methane so we could more than make up for the requirement. However, we found that the reason it was so high in the fluidized bed reactor was because the recycle line we had was too small in size, and we were losing a lot of energy in recycling through that. So by increasing it, which we have now done, we expect the energy requirement will be quite a bit less. So this may be only 13% of the energy required in an aerobic system to treat it, and at the same time we're producing energy, so we have a surplus of energy. Another interesting thing from it, which we thought about, some of my colleagues at Stanford looked at this and they said, well, now you're producing twice as much energy, you're getting electricity from it, only about a third of that energy in the methane goes to electricity, 2/3 goes to waste heat. So you got twice as much waste heat in your system, and you got the biosolids are in half. So we got more waste heat, we got less biosolids, and they figured out you could dry it. You could essentially get dried biosolids. They said if you burn it in a treatment system, if you could even get more energy because it's already dry, and you can burn it, or you could have a very small amount of biosolids to get rid of. So this is another huge advantage of that system, which adds to, reduces the cost. The interesting thing in the fluidized bed reactor compared to the gas sparge, where you have all the organisms mixed together, is this. The problem in wastewater, the reason we need the membrane when we're dealing with wastewater, is the volatile suspended solids, not the soluble organic material, but the volatile suspended solids that come into the reactor. They're very light, they're small, And they are mixed around in the system. They're not part of the granule activated carbon. They're not part of the bacteria. And they're circulating around through the system. Well, you notice here on the lower right there, in the red, it shows that's where we waste. We waste our biosolids. It comes from there. And we don't waste the organisms. We waste the biosolids. We can waste the biosolids independently of the organism in any way we want. Now, to make this thing efficient in the wintertime, you have to have a solid retention time, if you know that concept, of the organisms, of something maybe in the range of 100 days or so to get good efficient treatment in the wintertime. If you had all these volatile suspended solids in there, and they had to remain into a high concentration, you'd have a big high concentration of biosolids in the reactor, much higher. We only had in the suspended material only about a 500 to 1,000. This typical anaerobic system, they have 10 times that. And if they made a short detention time like we have in here, hydraulic retention time, it'd be even higher. That affects the viscosity, that affects the energy requirement, affects membrane fouling. And so this is another advantage in this particular system. Now another disadvantage I want to show is something we've got to face yet. And here's a COD bounce, because that's important to know what's happening here. One thing you can see, you've got sulfate reduction. So if you got sulfate in there, the sulfate's going to be reduced to sulfide. It's going to oxidize some organic matter, and that won't go to methane. So you lose some methane depending upon how much sulfate you have. But you'll see that under these very dilute conditions, that most of the methane in the wintertime, now this isn't cold time in the wintertime, gas is more soluble. In the wintertime, over half, maybe 60% of the methane that's formed is in the dissolved phase. So when it comes out of the reactor, it's there. We've got to get it out of the dissolved phase. That's something we have to do yet. And only about 40% is in the gas, comes out as a gas. Now in the summertime, it's just about reverse. We've got about 60% in the gas with the concentrations that I'm talking about here. So we're going to put in some energy. We're going to lose a little bit of energy getting that methane out, but there are several processes that are possible to do that, and that's somewhere we need to go. Well, here's just a summary of the advantages of anaerobic over aerobic. And we see that it's energy neutral. We get half the biosolids production. We get enough heat and less biosolids so they can dry the biosolids. We get high removal of organics. And I want to show you one other thing which I want to emphasize is important. And here is Monterey County. You notice this is one of the best agricultural lands in the country. Grows up a major producer of vegetables and fruit for the country. It's right on the ocean, and by using groundwater so much, overusing groundwater, they got seawater intrusion. So how are they going to grow these wonderful crops that they do? And so they put the Monterey County treatment plant right there in the middle of the agricultural area. And with this, they just had an conventional aerobic system with filtration and disinfection, and that water then they could put it on the crops. They put it on here and showing artichokes, strawberries, lettuce, celery, broccoli, things that you eat raw, and it's a safe thing to do. It's been approved by the state. Watsonville has expanded, and you go there and see strawberry patches all around. The strawberries you're eating, if you ate any here, you probably got them from sprayed on with the sewage from up there, and very tasty. But the one thing you find here is that they do, at this plant, they do take their biosolids and they digest it in cogeneration. With that, they get about 50% of their energy. The other thing is, they don't have to nitrify. And so what they do is add to the crops the nitrogen and phosphorus. Now, I indicated the problem with nitrogen and phosphorus is another important one. Here, they're using them back where they should be using them. And what they get there, they get the water for irrigation, they get the low energy production, they get the nutrients, and they don't have to oxidize them and throw them away. They use them for what we should be using them for, and that's as a fertilizer. Now, what we want to do is achieve all that. The system I showed you achieves all that at the same time. Instead of 50% energy savings, we produce energy, and that's the big advantage. But I want to show you another advantage. If we look at the treatment plant there in Monterey, it shows what it looks like. It's an aerobic treatment plant. And if we put the anaerobic MBR in there, that's its footprint, that little thing there. Because we have membranes. On the left there, you see the settling tanks. We don't need settling tanks. Down at the bottom there, they've got sand filters. We don't need sand filters. The membrane does that for us. You see the digesters over on the right? We only need half of them. In fact, now we're going to start treating not primary sewage, but raw sewage, and maybe screened raw sewage. And we may even cut that out because we'll be doing all the digesting right in the same reactor that we're doing for the treatment. So I think this is another major advantage of it. This is a pilot scale in Singapore where they're doing it as well there. It's a very efficient treatment plant. And I want to show at Stanford University, we are now building this particular, what's called Codebounce Resource Recovery Center at Stanford University. It's so hard to get any money in the United States. We have to go overseas to get all our studies done of this kind. The United States does, government and so forth will not give you any money for such things as this. But Stanford University see the value of it here in California, where we need to reclaim all the water they can. So this is connected right to the Stanford on the sewers coming from the students and the faculty housing. And they're going to treat it, and we're putting in a pilot plant there. So we'll have it in the United States finally. At least we'll be running a pilot plant just like we've shown here. We want to improve it. These are the first ones ever done. And so we have some ideas where we can do it better. And then we have a group of trailers that we're going to, any of you have a treatment plant, you'd like to really try this out once we go out there, we can put a smaller unit in these trailers and take to your treatment plant so your operators can see it and you can see it and demonstrate it. We have other processes that Craig and his group are developing that will also be tried, such as new methods for nitrogen, getting nitrogen out and so forth, and making other kinds of products. So this is something that we hope will expand and bring this technology to open to the United States so that we can get it developed, and hopefully one of these days we'll find someone that's bold enough to take the big step to go from this. We go on from the laboratory up to the pilot scale. That's 1,000 times scale up. We got to take the next one. The next 1,000 times scale up is going to be a full-scale plant to make sure it'll work and really get demonstrating so people can see how this kind of a system works. So in conclusion, I just want to say we can complete an efficient anaerobic MBR treatment of domestic wastewater is now possible at temperatures, wastewater temperatures down certainly as low as 8 degrees Celsius. We produces energy instead of consuming it. It reduces biosolids production, it reduces footprints, and it removes trace organics much better than an aerobic system. Anaerobically treated wastewater reuse, I think in landscaping and agriculture where we can get the nitrogen is one of the cheapest ways to go. And while everybody wants to ask me about how you're going to remove nitrogen phosphorus, I say, well, we'd like to find out how we can capture them, not remove them, not throw them away. I think that's important for us in the future if we can't use it on agricultural lands or something like they're doing in Monterey. In any way, we don't have to use organics to get rid of nitrogen because with the Anamox process, it doesn't require organics. It requires only about 40% of the traditional aerobic denitrification systems, and so there are other approaches there as well. I want to acknowledge the financial support I got from the Korean government. Thank you.
For an excellent talk. We have time for a couple of questions, please. There's a microphone coming here.
Perry, this is Jean Abreu, Kennedy Jenks again. Great presentation, thank you. I've been following it for a while, and it just seems like it's really maturing, and especially the surprising results, but very encouraging results of the contaminants of emerging concern being removed in your reactor there. But that's not my question. My question, and you touched upon it a couple times, and could you just elaborate a little bit on what the plan is, because we know you always have a plan, on the fate of nitrogen through these reactors, and for for potential utilities that don't have the advantage of being in the middle of an agricultural land like Monterey, if there's a discharge component to it, and what do you do with the ammonia?
Yeah. Well, that's a good question, and the one that commonly asked around here because of the requirements on that. Of course, on phosphorus, chemical precipitation has always been used, and that works on this as well. The nitrogen, I think, if you have to throw it back up in the atmosphere, the Anaerobic process, which is now used on recycle streams because of concentrated, it's the same thing. The organisms grow slowly. Well, people say it's got to be a concentrated stream, it's got to be high temperature. That's nonsense. It doesn't have to be. We just have to develop reactors like this kind here, where we can, and we've shown, others have shown, that you can treat low concentrations of ammonia efficiently at maybe an hour detention time, even in something like you have here. And the Anaerobic process doesn't take organics. It only takes about 40% of the oxygen, because you take half the ammonia and oxidize it to nitrite. That's all the oxidation have to, half the ammonia. The other half, the ammonia, then you combine with the nitrite, and it converts it bacteria. The Anaerobic organism will take that and convert it into nitrogen gas. Now that's, so much better than the aerobic system we traditionally have been using, and I think in the future that's become. Now, Craig Criddle at Stanford has developed something called the can-do process, where it's interesting, converts the nitrogen into N2O, which we said that's really bad to go up in the atmosphere. But N2O is a rocket fuel, and so they just put that into the methane gas and burn it, and they get 25% more energy out of the methane with that. So that's another process. But I think the others are recovering the methane. We had a long time ago by ion exchange. You put to ion exchange clinotylite, for example. You can get it on the clinotylite, and then you've got the ammonia. And instead of going through this energy cycle, if we want to think of the world's energy, we shouldn't be putting all that energy to take out of the atmosphere if we can put it in a form and directly on the land. I think that's a much better way. I think we got to think more in that terms.
Other questions? Let me ask you then, while other people think, a quick one. This looks very promising for municipal water treatment. How do you envision implementing in an existing facility? Is it something that you could easily retrofit the bioreactor, or would you need to completely replace it with a completely new system?
Well, that's certainly a good question, and that's what people want to say, well, I don't want to build another reactor. Let me give you, we got to start someplace. Okay. Where's a good place in California to start it? We got a kind of small one. If you want to build how about we got all these golf courses that are using drinking water and putting on the golf course. An ideal one was do it dispersed, throughout a treatment system near a golf course. Let's reclaim it that way at a golf course, and get these things system working. Landscaping and so forth. I think if we keep it away from the main treatment plant and put it where we can get the water and not have to send the water uphill or all these other things, that's the way to start. Now, treatment plants, they're wearing out. They got to tear them down, reap out the thing, and they got a lot of land around it. So land's more expensive than the rest of it anyway. But I think we got to start. This is day one, and let's start someplace at a small treatment plant. Make sure it works. Make sure we can prove what the cost is and so forth, and let's build from there. It's hard for me to jump from there to the 100 million gallon a day plant at this point.
Other questions from the audience?
Yeah, this is Rhodes Trussell.
Yes.
A couple questions, Perry. One I know, naive question that I want to ask. Well, let me ask them in the opposite order. So the first question, not so naive, I hope, is these two reactors you're using. Why two? And can you give us a little more of an understanding of how you went through it quickly, but I didn't quite catch it all. How the decision making went that resulted in the second reactor being a little longer HRT, and what you're doing to reduce the energy, because it looks like those are key decisions in the design of this thing, if I understand it right.
Okay, the reason we had two reactors is because that's how we did it. You got to start someplace.
Yeah.
And so then everybody asked, well, do you really need two? Well, you don't need two. But the other thing we came to is that we never did any cleaning of the membranes in this one we had in the field. And we, in the laboratory, it was easy to do it because we take out the membranes easy and clean them and so forth. But in the field, what are we going to do with the bacteria that are in there, and you're going to clean with chlorine dioxide, 1,000 milligrams per liter, and citric acid? It'd kill the organism. So we got the first one, and we got a line now that we can just pump the GAC into the first one and clean the membranes and then put it back. So at the moment, it's a good place to store it. Second, when we start up, we usually use that first one to start growing the granular activated carbon. I give you a lot of put. In some place, one of the things in a membrane bioreactor, you want to have the highest flux you can. One difficulty is you like to have a constant flow, and a constant flow at the higher flux. And so what happens when you get flows that are going up and down? And one thing you can do is you can put it through that first reactor at a much higher flow rate and take that out, and it's partially treated, and then maybe you can do something else with it. But it would allow you to, depending upon what your requirements are. But I think right now it's just flexibility. You can do it in one, but you would increase, you would have to, at some point, in the laboratory we did it in 2-hour detention time, 2 hours. The domestic sewage at 10 degrees, and it worked. Now, I think 2 hours is really short, and but the energy cost is in that second reactor because we need more GAC and we have to cover the membranes. I'd like that second reactor to be as small as we can to reduce the energy cost in it. But if I need more time with the organisms, then that other reactor, I can make that any size I want, and gives me a total detention time of the wastewater in the system. You might look at it similar to, if you look at an aerobic membrane bioreactor, most of them today, they have the reactor, and then the membranes are in a little separate unit, and that's they can chemically clean it and everything like that. And I think that makes sense to look at the overall hydraulic retention time and how you're going to divide it between the first one and the second.
So the logic really has to do with cleaning the membranes.
Pardon?
The logic really has to do with being able to clean and access the membranes without killing
you really need to clean it. I think you got to be able to get the GAC and put it someplace.
The second question is a broader one where I'm going to expose how naive I am about this. So I went through my education on these things in the 60s, and Professor Oswald particularly had a beautiful little diagram he always did for anaerobic and aerobic processes, and the end products were different. And I just want to understand, what are the end products from this thing, and can I get the same places I can with an aerobic process, or can't I, or how do they are there any fundamental differences that we need to be concerned about or understand?
Well, the effluent COD, when we're
not
working,
COD, the kinds of chemicals.
But that's the kind of, and most of that is refractory. The biodegradable portion is small. We can anaerobic, I don't know what's going on with these trace organic, these kind, but we know that chlorinated solvents, aerobically you can't degrade them, and anaerobically degrade very well, and our bacteria live on them. So there are differences. In the past, when I first started, it was, if it can't be done aerobic, it'll never be able to do anaerobic. And I told my first student, he came in and wanted to do pesticides anaerobically, and I laughed at him, but said, go ahead. And so he found lindane, DDT, epoxide, and so they all were broken down anaerobically, and you couldn't touch them aerobically. So they're,
I remember that work. Yeah.
Which is better. So I think you just have to look at the effluent and see, but overall I can't, study it. Someone's got to study it, I can't tell you what might come up that is a bad thing.
Well, I just want to make one final comment. It's really great at your stage in life to come up with such an incredibly innovative idea. Congratulations.
And
it's a lot of fun.
With that, let's thank Professor McCarty for an excellent talk.